Watch out, Hammy. Hey, Robert, how's it going?
Hey, I'm good. Yourself?
Doing good, man. Doing good. What can I do for you?
Good. I was wanting to know if we could just look over a couple of questions.
I'd be happy to.
Can I do screen share or no?
I think I might prefer to keep it like this. If you don't mind, I'll turn on my screen sharing QCam and we can navigate through if that's okay, because I'm expecting somebody else to come in who's got a makeup test. I need to be able to take over right away to get her squared away.
Okay, yeah, that's fine.
But let me launch QCam here. Which homework set are they from, Robert?
Homework 8, number 4. It was giving me some issues.
All right, let's look at that. Oh, that's bullshit. Well, that's going. We got the camera connected. Grace is here. Still no sign of Neon. All right. So we're going to homework 8, number 4. Pen working? I think this pen works. Okay. If anybody sees Niana Wing pop in here and I'm not paying attention, please grab my attention and let me know, because I got to work with her on something real quick. You said problem 4, this one?
Yes, sir.
All right. So we want the limit as x goes towards pi over 2 from the right in cos x over 1 minus sin x. Hammy, you gotta move, bud. I need to get in here. I'm sorry. I know. You're very sweet and you're very handsome, but you gotta move.
Come here.
Sorry, my dog's in my way.
Hammer.
He's getting used to being able to hang out under here these last few days. All right. So we're calculating the limit as x goes to pi over 2 from the right in the expression cosine x over 1 minus sine x. So first, Robert, can you explain to me, why is this limit challenging? What's going on here? What does this limit look like if we just plug in pi over 2?
Well, cosine of pi over 2 is 0, and 1 minus sine is 1 minus 1, so it's 0 over 0.
Excellent. All right. So this, this looks like 0 over 0, which is certainly a problem. So what can we use for that?
Well, it's an indeterminate factor, so you can use L'Hopital's rule, can't you?
Yeah, exactly. It's the right kind of indeterminate form. It's an indeterminate ratio, indeterminate fraction. So we can use L'Hopital's rule. So I'm going to differentiate the top and differentiate the bottom and try again. So I'll say, by L'Hopital's rule, this is equal to the limit as x still going towards pi over 2 from the right. The derivative of cos x is what?
Negative sine.
Good, negative sine x. And then downstairs here, I'll have the derivative of 1, which is 0, minus the derivative of sine x, which is cos x. So this looks like lim x to pi over 2 from the right of sine x over cos x, right? Because the negatives go away. We've got a negative upstairs, negative sine x, and negative downstairs, negative cos x. So at a glance, if you still try to plug in pi over 2, this doesn't look beautiful, right? The sine of pi over 2 is still 1. The cos of pi over 2 is still 0. So this looks like 1 over 0.
And I plugged that in and it wasn't correct.
Yeah. So what is 1 over 0?
Well, it's DNA. It doesn't exist.
Sort of. 1 over 0, I think you take 1 and you divide it by a very, very, very small number. it's true that 1 over 0 itself does not exist. As a number, that's not a thing, right? We can't divide by 0. But we're thinking here about limits. So the way I encourage you to think about this is the top is very, very close to 1, and the bottom is very, very close to 0. If you take a number very, very close to 1 and you divide it by a number very, very close to 0, we get a very, very big number.
So we'll just go to infinity?
Yes, sir. And one way you can think of this, oops, sorry, is that sine over cosine, that's tangent, right?
Mm-hmm.
If we look at the graph of tangent, I'll even just type it like this, over cos x. As x goes towards pi over 2, let me put in the pi over 2 line here. I'll put it in as a dotted line so we don't confuse it with the graph. If I'm marching along the red graph, getting closer and closer to pi over 2 from the, where are we going? We're going from the right. That means I'm over here coming towards this line. We're actually going down to negative infinity. And the way to see this is if you think about these guys each on their own. I see Nyana just came in here, so I'm gonna have to be very quick about this. Here's sine, here's cos, here's pi over 2, right? Oh wait, no, on cosine, yeah, that's pi over 2. Here, pi over 2 is up here. So if I'm approaching pi over 2 from the right along cosine, I'm going towards 0, but I'm also negative. And some people like to write that like this.
Mm-hmm.
So this is like 1, it's like 1 over 0, but the bottom is negative. So I would call this negative infinity. No, I have not fed her yet this morning. So
Okay.
kind of 1 over 0 minus is like infinity, but it's negative because of the minus. And that's because the cosine here is going to 0 in a negative fashion.
The easiest way for me to think about it is a tangent function.
Yeah, the graph of tangent is definitely the easiest way to do this. All right, I got to Nana just showed up. I've got to get her set up for a makeup test. So I'm gonna talk to her and be busy here for just a second, but then I'll come back and work more with you guys.
Okay.
Let me get a breakout room. Hey Nana, how are you doing?
Hi, how you doing?
I'm good, I'm good. Are we all ready to go?
Yes, I am. Can I just go? Do I go into the exam 2 makeup, right?
That's where you'll be going, but before you get there, I'll ask you, I'm gonna assign you to a breakout room here. I'm gonna assign you to room 1. Go ahead and hop into that
Okay.
breakout room. And then once you're in there, you can get started.
Okay, thank you. And is there a password?
There is, but HonorLock will take care of all of that for you. So once you sign into the exam,
Okay, cool. All right.
HonorLock will launch. You'll go through all of that, and it'll input the password.
Sounds good. All right, thank you.
All right. Before you go, do you have your calculator? Oh shit! All right, I gotta hop in there after her real quick. Breakout rooms. Join. Hey, sorry about this. I'm chasing you in here. Do you have your graphing calculator? Anything that you need?
Yes. Do you need to see my work area?
I would like to see the work area, and then that looks like a scientific calculator. Do you have like a TI-83 or 84, something you can use to graph functions?
I don't. I have to actually buy one. I was gonna get it this week. I actually just got my paycheck today, so I'm just gonna get it today. But I've been using it's the TI-36X Pro.
Okay, so that will be okay, but there is a question on here that's going to require the use of a graphing calculator. So when you get to that question, let me see which one it is. I'll just ask you to raise your hand here in Zoom, and then I'll come in and I'll graph the function for you on my 84. It is, where is it? I think it's question 9.
Okay.
Yeah, when you get to question 9, raise your hand in Zoom, and I'll come in and graph that function for you on my 84 emulator, okay?
Okay, cool. I'll be able to see it on the screen and everything like class.
Yep, just like class. Yep. All right, cool.
All right.
Good luck. Okay, so we're back. Yeah, are you comfy with that one, Robert? Thinking about the graph of the tangent function, or thinking about it as like 1 over 0 minus, that kind of thing? Is there anything more we want to say there?
Yeah, so if you go back to it in Desmos, why do you look at it from, not from where 0 is, but where pi over 2 is?
So if we look at the problem, they're asking us to take the limit as x goes to pi over 2, right? pi over 2, and we're doing it from the right. So then in Desmos, that means here's pi over 2, right? This blue line, this is x equals pi over 2.
Mhm.
And I can approach from the left, coming in like this, or I could approach from the right, coming in like this.
Okay.
The
Positive.
plus here tells me to come in from the right. So I want to sneak in from this way. So that means I'm along the red graph coming towards this from the right.
Okay. I see it now.
Cool. All right. I think Katie came in after Robert, and then Fabrice came in after Katie. I believe that was the order. So I'm going to give the next question to Katie.
It's on homework 8, number 12.
Okay, actually, I think I have homework 8 up over here. Yeah, this one, tan 4x all to the x.
Yes.
This is a tricky one. So we want the limit as x goes to 0 of the tangent of 4x all raised to the power of x. What have we tried so far, Katie?
I got all the way like down to the LH rule,
Okay,
but then when we have to do it again, taking the derivative of the top one was what confused me.
all right, well, let me get caught up with you then. I'll say f of x is my function here, tan 4x all to the x, so that the natural log of f of x is the natural log of tan 4x all to the x, which is x times the natural log of tan 4x. So then instead of this, I say, okay, the limit as x goes to 0 of the natural log of f of x is equal to the limit as x goes to 0 of x times the natural log of tan 4x. And if we tried to send x to 0 here, this would be like 0 times the natural log of 0, which is 0 times infinity. So we shove the x downstairs, and that will get us to a place where we can apply L'Hopital's rule. So this will be the natural log of tan 4x divided by 1 over x, like this, right? And you said you were at the step after this, where you use L'Hopital's rule?
Yes, I did L'Hopital's rule, and then it came out to be another, what do they call
Yeah,
it?
it's still indeterminate, right?
Yeah.
So one application of L'Hopital's rule gets me lim x to 0. The derivative of ln of tan of 4x is 1 over the tan of 4x times the derivative of tan 4x, which is secant squared of 4x times 4 by the chain rule. And downstairs, the derivative of 1 over x is negative 1 over x squared. Good so far?
Yep.
All right, so then I'll continue this. I think it's, even though it's true that we need a second run of L'Hopital's rule here, it's wise to take a second and ask ourselves what's going on as I send x to 0 in this expression. In other words, can I clean things up at all? So if I try to clean this up, lim x to 0, upstairs I have 4 secant squared 4x divided by tangent of 4x, and downstairs I have negative 1 over x squared. And the secant squared of 4x over tangent of 4x, there might be some cancellation we can do there, right? Secant squared of 4x, so this is going to be nasty, isn't it? This is 4 times 1 over cos squared 4x times cos 4x over sine 4x, because we're dividing by the tangent. And then downstairs here, I have -1/x². I can cancel one of the cosines. And we'll get lim x to 0.
I can't see the writing because of the little screen.
Sorry, yeah, here, let me get this out of the way. So sort of here's the algebra step I'm doing here. So secant squared, this 4 is this 4. And then secant squared of 4x is 1/cos squared 4x. I'm dividing that by tangent of 4x. So staying in the numerator, I'm going to flip and multiply. Tangent of 4x would be sine 4x over cos 4x. So when I divide by that, I have cos 4x divided by sine 4x. So this piece is the divide by tangent. This piece is the cos squared of 4x, and this is just the 4 that was out front. This cos 4x can cancel with one of the cosines downstairs, but that's all going on in the numerator. So I end up with 4 over cos 4x times 1 over sine 4x, and all of this is being divided by -1/x². So basically, when you get to this stage, you want to clean everything up algebraically as much as possible. Do you see anything I can do with those pieces?
Well, can't you move the x² up?
Yes. Sorry, I want to get some water. Yes, you can. The x² can come upstairs. So if we do that, then this will be, how do we want to write it? I'll write it just really carefully like this. 4/cos 4x times 1/sine 4x times -x²/1. And then we've got some choices how to proceed from here, depending on how clever you're feeling and how many of those special trig limits we remember from the start of the semester. But I think the most natural thing is to observe that as x goes to 0, cos of 4x goes to 1, right? So let's look and see which pieces are problematic and which pieces are not. This piece is not a problem, because this is just going to 4/1. The cosine of 0 is 1, so this piece goes to 4/1. This piece is a problem. This piece looks like 1/0 as x goes to 0, because the sine of 0 is 0. And this piece is going to -0/1. So kind of this first piece isn't an issue. I'm not worried about this piece, but I am worried about these pieces. So what I'll do here is I'll say, okay, this piece is going to be dealt with separately. I'm going to use my limit laws. And over here, I'll combine these two pieces. Like that. So these two pieces here became this piece. And this guy, I'm just pulling him out and dealing with him separately. Remember those limit laws? The limit of the product is the product of the limits.
Yes.
All right. So that first piece is 4. This whole thing here, this is 4. So I'll have 4 times the limit as x goes to 0 of negative x squared over the sine of 4x. And this piece looks like 0 over 0. Right? This piece again, I don't know, there's not a nice notation because I can't really say it like that. But this piece looks like 0 over 0. So I'll apply L'Hopital's rule to it. The 4 just coming along for the ride. He's not getting L'Hopital. This is the only thing getting L'Hopital. I have lim x to 0. The derivative of the top is negative 2x. The derivative of the bottom is cos 4x times 4. And now finally, when we take our limit, this is 4 times 0 over 4. Right, if you want 1 times 4 downstairs, right? The cos of 4x, that piece goes to 1 because cos of 0 is 1. This 4 is this 4, and negative 2 times x, that goes to 0 as x goes to 0. And 4 times 0 over 4 is just 0.
Could you go back up top? I just want to see something. Yeah, on the first page.
Here's the start.
How did you get negative 1 over x squared?
I'm taking a derivative. So this is the stage where I'm using L'Hopital's rule. So this is the derivative of the top, the derivative of the natural log. I can show the derivatives off to the side here. If I
Yeah,
take,
I had a question on that one just above it. How'd you get the 1 over x underneath?
I shoved this guy downstairs as his reciprocal. So this piece
Mhm.
becomes this piece. Like multiplying by 2 is the same as dividing by 1/2.
Mhm.
Multiplying by x is the same as dividing by 1 over x. It's our trick for turning indeterminate products into indeterminate ratios. Let me answer the derivative question, Robert,
Okay.
and then I'll show you in the book where this is kind of introduced. So if I take the derivative of the top, just for completeness' sake here, the derivative of the natural log of tangent of 4x, that's 1 over the tangent of 4x times the derivative of tangent of 4x. That's how we differentiate the natural log function. And then the derivative of tangent 4x on its own is a chain rule thing. So the derivative of tangent is secant squared, so secant squared of 4x. And then I need to multiply by the derivative of the inside here. The inside here is 4x, his derivative is 4. So that's where the derivative here is coming from. And the downstairs piece, d dx of 1 over x, that's the same as d dx of x to the negative 1, which is negative 1 times x to the negative 2 by the power rule, which is negative 1 over x squared. I didn't show the steps on those because we've kind of been doing them a lot, but yeah, this is where each of the derivative pieces is coming from. Do we all feel comfy with where the bits here came from?
Mhm.
Our first L'Hopital? All right, then let me really quickly jump into the textbook and I'll show you, Robert, where this is coming from in 4.4. These are kind of, there's a handful of really useful tricks. Indeterminate forms are a bitch and a half, basically. The only ones that are really nice are 0 over 0 or infinity over infinity.
Mhm.
And because that's where we can apply L'Hopital's rule. If the fraction looks like 0 over 0 or infinity over infinity, then we're Gucci to apply L'Hopital's rule. But if it's anything else, then we need to turn it into one of those. And kind of the first special indeterminate form we saw besides 0 over 0 or infinity over infinity were these indeterminate products, where you've got two functions, f and g, multiplied, and one's going to 0, the other one's going to infinity, something like that. The way they handle this is by saying, okay, f times g can be rewritten as f divided by 1 over g, or g divided by 1 over f. And that's exactly what I'm doing here.
Okay, so you're turning it into something a little bit easier to work with.
Exactly. Yep. Right here, I've got an indeterminate product to which I cannot apply L'Hopital's rule. But I know if I shove this piece downstairs as its reciprocal, and that's that f divided by 1 over g, then I will have a fraction and I can apply L'Hopital's rule to that. Really, I should be checking that this is an indeterminate form. I should check that this is like 0 or infinity over infinity. But since Katie was already on the second L'Hopital rule step, I was just kind of trying to catch up here.
Yeah.
But yeah, that's it exactly. So at this stage, I would check and say, oh, this is like 0 times infinity. So then I'm going to shove the x downstairs, and now this will be like infinity over infinity. And now I can take my L'Hopital's rule derivative stuff. All right. Katie, did you need to see the bottom of this anymore?
Yes, I want to take a screenshot.
Yeah. All right. So here, if you want to cap the start, here's the start.
Okay.
And then, let's see, maybe we'll go up to the next L'Hopital's rule. So here's the middle.
Okay.
All right, and we're actually not done yet. We still need to finish. So before you screen cap this last bit, let's finish things up. So what we've shown here is that the limit as x goes to 0 of the natural log of my function is equal to 0. Therefore, the limit as x goes to 0 of our function should be e to the 0, which is 1. So this is actually our answer, i.e. lim x to 0 tan 4x all to the x is 1. All right, and there's the final step.
Thank you.
Of course. All right, I think Fabrice and Tahara haven't gotten to answer or ask a question yet. Fabrice was in here, I think, before Tahara, so I'll go to you next. Sir, what can I do for you?
So I was thinking about number 15.
In homework 8 here?
Yeah.
All right, let's take a look. Okay. These do tend to take a little while, so I'm going to try to kind of slim down the procedure, right? This is where you go through all those steps, A through H, and then use that to sketch your graph. So,
This the one that you have to do all those steps for them before you find the.
yeah,
find
it
the
is.
graph.
Yep. So I'm going to run through this very quickly, and then we can take screen caps and kind of review. First, we need to find domain. This is a polynomial. So the domain is all real numbers. Then we want to find intercepts. The y-intercept comes from plugging x equals 0. So when we plug x equals 0, we get y equals 0 cubed plus 6 times 0 squared, which is just 0. So the y-intercept is 0, 0. X-intercepts, we set the function equal to 0. We need to solve 0 equals x cubed plus 6x squared. And the way we solve that is by factoring. I can factor an x squared out. I get x squared times x plus 6. So I have 2 x-intercepts. One of them comes from this factor. Let me get this out of the way. X equals 0, that's 0, 0. It's the same as our y-intercept. And the other one comes from this factor, setting this factor equal to 0, we get x equals -6. So that's domain and intercepts. What was next? Is it symmetry?
No, it was,
Or asymptotes?
nope, yeah, you're right, symmetry.
Symmetry. So this function has both odd powers of x and even powers of x. So as a polynomial, that's the shortcut, right? This one is neither even nor odd.
So I have a hypothetical. What if they were both x squared?
Well, then it would be a silly way to write this. If you had x squared plus 6x squared, that's just 7x squared.
Yeah,
That would certainly be an even function. So for polynomials, the trick is if all the powers of x are even, then it's an even function. And if all the powers of x are odd, it's an odd function. For rational functions, other slightly more complicated functions, it's not so simple. But for a polynomial, it really is that simple. So we don't have any symmetry. It's certainly not periodic.
also, is this how you're going to present it in the test with the 4 multiple choice, or are you wanting us to actually draw it out and then just type in an answer?
No, you guys will need to draw the graph. Yeah. Yeah. So probably what I'll do is I would say, I'll give you a few of these, like I'll give you the domain maybe and the intercepts and the symmetry, and then I would ask you guys to do the rest. So I'd say, here's this function, its domain is this, its intercepts are this, its symmetries are this. Find the asymptotes, increasing, decreasing, mins, maxes, concave up, concave down, and then sketch the graph. Something like that. But I'll slim the problem down so you guys don't have to do everything, because I know there's only so much time on the test. But the main thing I want to see you guys doing is the calculus steps, right? Where you take the first two derivatives and figure out where you're increasing, decreasing, mins, maxes, concave up, concave down, inflection points. And then I want to see you drawing the graph. Again, this is a polynomial. So it has no asymptotes. But it does have end behavior. The end behavior, because it is an odd degree polynomial, it'll go up on one side and down on the other, one of these two. It's an odd degree and the lead coefficient is positive. So that means as x goes to negative infinity, y goes to negative infinity, and as x goes to positive infinity, y goes to positive infinity. In other words, I may not have asymptotes, but I know on the far left it goes down and on the far right it goes up. I don't yet know what happens in here, but I know that those arrows are like this, right? So that's what, for polynomials, that's kind of the best thing we can do for asymptotic behavior. I'm probably messing up these labels, but I'm going to go after mins, maxes, and increasing, decreasing next. So that means I need my first derivative. Y primed here is 3x squared plus 12x, which can be factored as 3x times x plus 4, right? Yeah. So my critical numbers are x equals 0 and -4. So I'll draw a number line here for y primes. And I'll put -4 on here, put 0 on here. And then we'll need to test something from each of these regions, right? So to the left of -4, I could test like -5 or -6. I say I plug -5 in here. Then this would be 3 times -5, which is -15, times -1, right? -5 plus 1 is -1. So -15 times -1 is +15. So y primed of -5 is +15. So we're increasing. Y primed is positive here, which means we're increasing. between -4 and 0, I could test -1. 3 times -1 is -3. And then -1 plus 4 is +3. So this would be -3 times +3 is -6. Y primed of -1 equals -6, which is certainly negative. So we're decreasing between x equals 0 and or between -4 and 0. And then to the right of 0, I could test 1. Y primed of 1. If I plug 1 in here, I'll have 3 times 1, which is 3, times 5. So that's +15, which is positive. So we are increasing, decreasing, increasing, which means we have a local max here. And we have a local min here. And I'd like to find the min and max values. So the max at x equals -4 is, I just come back up to the original and I plug in -4. Y equals -4 cubed plus 6 times -4 squared. -4 cubed is -64 plus 4 squared. Let me see. Oh, is this going to be bigger? It is. So 4 squared is 16. 6 times 16 is 96. And if I subtract 64 from that, I get 32. So the local max here is -4, 32. And similarly for the local min, the min at x equals 0 is y equals 0 cubed plus 6 times 0 squared. That's definitely 0. So 0, 0, which is our x, one of our x-intercepts, also our y-intercept happens to be a min as well. We good so far here? Maybe I'll hold for a second, you can catch up writing. Next, we're going to do the second derivative, concave up, concave down, and inflection points.
Can you talk about asymptote again? Can you go back to that?
Yeah, sure. Give me just 1 second. We'll talk about that. So this is a polynomial, which means it doesn't have any asymptotes, but it does have end behavior. And I'll talk about that in just a second. All right. So we want to talk about the work we did under asymptotes, where we said there isn't any asymptote, but I can discuss the end behavior. This, for polynomials, this isn't something I've talked about explicitly in this class because it's supposed to be a part of pre-calc or college algebra, but I think sometimes it doesn't get treated very well, so I don't mind doing it here. There's only a few possibilities for polynomial end behavior. Every polynomial in the world has end behavior either like this, up on both sides, right, with some, who knows what in between, or down on both sides. Right, maybe like this, who cares? Or up on the right, down on the left. Or the reverse of that, up on the left, down on the right. So these are the 4 possible end behaviors for a polynomial. And it's determined by the degree and the sign of the lead coefficient. This is an even degree. So like the biggest power of x is x squared, and a positive lead coefficient. This next guy is an even degree and a negative lead coefficient. This fellow is what it looks like if you have an odd degree and a positive lead coefficient. And this is what it looks like if you have an odd degree and a negative lead coefficient. So kind of the things to think about, this kind of looks like how x squared looks, right? X squared goes up on both sides. That's an even degree and a positive lead coefficient. These arrows, I'm not paying attention to anything in between, just the arrows on the ends. These arrows look like what negative x squared looks like. That's an even degree and a negative lead coefficient. These arrows look like the end behavior for x cubed. That's an odd degree and a positive lead coefficient. And these arrows look like the arrows for negative x cubed. That's an odd degree and a negative lead coefficient. The main idea here is that for very, very large values of x, it's just the lead term, the highest power term, that really determines the shape of the function. So near zero, the other terms matter, but very, very far away from zero, the other terms don't matter. And I can show you in Desmos kind of what I mean. So here's some fairly complicated polynomial, right? But look at the lead term, the x to the 4. That's the dominant term. Because that power is even and the coefficient of x to the 4 here is 1, which is positive, this thing eventually goes up on both sides. If I were to make this lead term negative, all sorts of shit's going to change, but now it's going to go down on both sides. If I make this a 3 instead of a 4, now it goes down on the left and up on the right. And that coincides with this picture. Odd degree, the degree is 3. Positive lead coefficient, the lead coefficient here is 1. If I made that a 2 or a 5, it wouldn't change things, even though 0.01. We're still eventually going to have this same end behavior. We might have to zoom way the fuck out to see it, but here it is, right? We're going up on the right and we're going down on the left. So the end behavior is determined just by the lead term. So that's what's going on here. So the polynomial end behavior, if you're graphing a polynomial, polynomials never have asymptotes, but it's useful to know which way the arrows are going to point, right? It's useful to know what's going to happen far away from 0. That kind of gives me a good starting place for the graph. Does that make sense, Fabrice?
Yes.
All right, so you may want to, and I encourage anybody else here who's in Calc 1, especially if you didn't get a good treatment of this, you may want to take a screenshot of this page. Because this is a hugely helpful thing, and it's really easy to figure out because you just have to look at one term. All right, let's jump back into the problem. Everybody got a cap who wants one? Going away in 5, 4, 3, 2. So we've got our increasing, decreasing mins and maxes. I think this is both E and F in the book's guidelines. And then G and H are the concavity. So to come up with the concavity and the inflection points, we need the second derivative. Y double primed, Y prime prime here, the second derivative. Our first derivative was 3x squared, so I'll say this is the derivative of the first derivative, which was 3x squared plus 12x. So I need to differentiate that. And that's going to give me 6x plus 12. And so this thing will be equal to 0. Y prime prime equals 0 if and only if 6x plus 12 equals 0, which will happen if 6x is negative 12, which means x is negative 2. So my number line for y double prime just has one thing on it, negative 2. To the left of negative 2, I could test something like negative 3. Y prime prime of negative 3 is, get away. If I plug negative 3 in here, then this will be 6 times negative 3, which is negative 18, plus 12, which is negative 6. So this is negative, which means we are concave down. And if I test something over here like y prime prime of 0, if you plug 0 into the second derivative, you get 12, which is positive. So we're concave up over here. And then the last thing I like to do is make that last number line for the shape of the graph in each of these regions. So I'll make a big number line, and on this big number line, I'm going to put any information from the first derivative and any information from the second derivative. So the numbers from that first number line were negative 4 and 0. The only number on the second number line is negative 2. So I'll put negative 4, negative 2, and 0, all on this number line. Scam likely, go fuck yourself. And in each of these regions, I can discuss the shape of my graph. I'll either be like increasing concave up or decreasing concave down or whatever. Well, you guys are about to get a cameo from Nova Kitty here. He wants to say hi. He's grooving. Yeah, just doing his thing. All right. So everywhere to the left of negative 2, we're concave down. So I can come in here and say, okay, concave down, concave down. And then everywhere to the right of negative 2, we're concave up. So this is concave up, concave up. And then I can fill in my increasing, decreasing. From negative infinity to negative 4, we were increasing. From negative 4 all the way to 0, we were decreasing. So this is decreasing, decreasing. And then at 0, we switched back to increasing, which means the shape of the graph from negative infinity to negative 4 is increasing concave down. That looks like this. From negative 4 to negative 2, we were decreasing concave down. That looks like this. From negative 2 to 0, we're decreasing concave up. That looks like this. And from 0 to infinity, we are increasing concave up. That looks like this. And we've already identified these. This is a local max. And it's at the point negative 4, 32. At x equals 0, I had a local min. And this is the point 0, 0. We figured all that out on our first number line. What's going on here is an inflection point, right? I guess I should have put that up here. Because my concavity changes. I go from concave down to concave up when x is equal to negative 2. And so this is going to be at negative 2 comma something. And to figure out the something, I'll say my inflection point at x equals -2 has y equal to, what was my original function? X cubed plus 6x squared. So this is -2 cubed plus 6 times -2 squared, which is -8 plus 6 times 4 is 24. And 24 minus 8 is 16. So this is at -2 comma 16. So that inflection point I'll put down here on my shape. This is an inflection point at -2 comma 16. And now that I have this number line with all the good shit on it, I can draw my graph. So before I draw the graph, questions up to here.
No, I think it's pretty straightforward.
All right, so let's do it. Let's draw this graph then. Here we go. Give myself some big old axes. I want to pay attention to the scales. So I've got y values as big as +32 and nothing negative. So I guess I'll do something like this. This is the graph of y equals x cubed plus 6x squared that we're drawing. Some points that I know are on this thing. Well, these points I know are on this thing. So 0, 0 is on this graph. -2, 16. I'm going to mark this up here as 32, which means this right here is 16. I'll call this -1, -2, -2, 16 is on here. And -4, 32 is on there. So I'll call this -3 and -4. -4, 32 is up here. And then what else did we have going on? Got our min at 0 there. What were my x-intercepts? I had one out here at -6. So -5, -6. All right. I know that this should be a local max. I know that this should be an inflection point. I know that this should be a local min. I know that my end behavior should go down on the left and up on the right. This is a local max, so it should look kind of like this. This is a local min, so it should look kind of like this. This is an IP. This is an x-intercept. So let's do it. Here we go. And then I should stay concave down until I get to this, but then I switch to being concave up. And then I come around and do something like this. And that is a pretty good graph. You would want to label these points explicitly. So this is -4, 32. This is -2, 16. This is 0, 0. This is -6, 0. And that is a really nice graph of this function. Everybody see kind of how that number line informs the way we draw this graph? This piece over here is all kind of shaped like this. This piece in here is all kind of shaped like this. This piece in here is shaped like this. And this piece over here is shaped like this. And then these points are kind of what I use as my skeleton. I drape this skin over this skeleton. And the end behavior was really helpful also, right? Having this arrow, knowing that this arrow should go up over here and this arrow should go down over here, also very, very helpful.
What did IP mean again?
Inflection point. So that's a place where concavity changes. Here we went from concave down to concave up. But also we could have gone from concave up to concave down. So an inflection point is where your concavity changes, right? Everywhere to the left of this is concave down. Everywhere to the right of that point, the graph is concave up. Can you kind of see the difference in the shape here? Imagine you pour some water on top of this. It would all run off the side. That's what it means to be concave down. On the other hand, if you pour some water over here, it would all kind of pool up. That's what it means to be concave up. So this kind of bowl shape is concave up, and this kind of upside down bowl shape is called concave down. So that inflection point is the point where the concavity changes. Cool stuff, right? Okay, I want to be fair to everybody, and I'll hang out here just a little bit. I think Robert, Katie, and Fabrice have all gotten to ask a question. Tahara, you have not had an opportunity to ask a question yet. How are you doing?
Can I ask a question about the study guide?
You can. I don't want to solve the study guide problem completely because the point of the study guides is for me to see how you guys are doing. But if you have a question about a study guide problem, I can work a similar one or I can give you a hint. Sure.
Okay. I needed help with question number 2.
Okay, let's take a look. All right. I think. So consider the following problem. Box with an open top is constructed from a square piece of cardboard 3 feet wide. Like, oh yeah, this is a challenging one. I will go ahead and show you the setup here, okay? So normally I wouldn't do this, but I'll, because this is a particularly challenging study guide problem. Applied optimization is difficult stuff. In the same way that related rates is difficult, right? Because we have to kind of do this, they're all word problems. So I'm building a box with an open top, and the trick is I'm going to start with a piece of cardboard that is a square, and I'm going to cut out a little square from each corner and bend up the sides. So kind of, let's see if we can picture this before we jump whole hog in. I'm starting with a square. And the way I'm going to make this box, imagine I come in here and from each of these corners, I cut out a little square. So I cut this out, I cut this out, I cut this out, I cut this out. Then what I'm going to do is I'm going to, along these, I make like a little crease here, 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 and here. And then I fold these edges up. I fold these edges up. That would create a little box, right?
Yeah.
Can you kind of picture it? I'm looking down from the top now, and I'm going to fold these up. I'm going to fold these up. That gives me my box. They told me that the dimensions of the square with which I began is 3 feet by 3 feet. And they want to know, draw several diagrams, so blah, 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 draw a diagram, the general situation, an expression for the volume in terms of X and Y. So, so our box can have, find the largest volume it can have. Let X denote the side length of the square being cut out. Let Y denote the side length of the base. So we come back here. In order for this to fold up and create a nice box, these all have to be identical squares, don't they?
Yes.
Otherwise, the side lengths wouldn't match up. So we're going to call this X. If that's X, then this is X, and so are all the other little guys. And we'll call, let me make sure I'm saying this right, call the side length of the base Y, right? Yeah, okay. So the base of my finished box is this middle piece here. Right, after I fold this up and I fold this up, the bottom of the box is this piece right here. They want me to call this Y. So then they ask for a few things. What is the volume? Well, if you can picture this box after it's been folded up, I'll try to draw that here. After I fold up this box, it's going to look like this, right? Where this is still Y. And then my height, I'll try to draw like this, or whatever, that dimension, whatever you want to call it. Right, after I fold these in. So this dimension is still Y. This dimension right here is going to be X. So maybe I should have drawn that on this side. I should have, yeah, this is Y. So then my volume is what? It's the like height times width times depth. That's, if this is Y, then this is also Y, right? Because each of these four things are square, and we're starting with a square, the base here is actually a square. So this is going to be Y squared times X, this times this times this. And then your task from here is to maximize this volume function. And the way you're going to do that is first by getting rid of one of these variables. You have to find another equation. And I'll tell you, it all comes from just thinking about this side length here like this. So if that's Y, then this is Y, and this is also X. So kind of your constraint here is that X plus Y plus X has to be equal to 3. So we want to maximize this with the constraint that 2x plus y is equal to 3. This is kind of the setup. It's a little bit complicated, but this kind of gets you to that place that we begin all these other problems with, where you have a function you want to maximize, and then a constraint which allows you to eliminate one of the variables. All right, I think I have to move over and help Mayana with a test issue. If you guys want to talk more, hang out for a little bit. I will come back in just a second. We can talk a little bit more, but that is going to be about the end of the office hour. I hope you guys have a good rest of your day. If you decide to leave, if you decide to hang out for a minute, we can come back and talk just a little bit more in a second. Okay. Oh, did she leave? She left. She never asked for help on that one. Shit. Let me jump into this moderation. What the fuck is going on? Maybe she gave up. Where the fuck did she go? I guess she's done. Okay. Yeah, so that is it then. Sorry about that, guys. I was expecting my student who's taking a makeup test to have a question that I was going to help her with a little bit there because she didn't have her graphing calculator, but that is it from me today. Are there any burning questions? Anything I can help you guys with in parting before we go?
I wanted to discuss on the honors project.
That sounds like a really good idea. Let's do that. Before you and I start on that, Fabrice, is there anything urgent that we need to talk about?
I was thinking about number 27.
Okay, let me see if I can give you a little bit of a start on number 27. Is that your homework 8?
Yes.
All right. Let me see if I can give you a little hint there to get started. And then Tahara, you and I can talk a bit about the honors project. 7. All right. So this is, oh, sorry, screen share. That's what I wanted. This is the same sort of thing as the one we just did, right? Oh, sorry, come back here. So you're going to start by finding the domain. You're going to try to find any intercepts. You're going to identify any symmetries and asymptotes. And for this function, this is not a polynomial. This has a lot of that stuff. So I can give you a little bit of a start here. If y is the natural log of cos x, if we want to find the domain for a natural log, we know we need the inside of ln to be positive, right? We cannot take the natural log of a negative number. So to find the domain here, we need to solve the inequality cos x is strictly greater than 0. And the easiest way to do that is thinking about the graph of the cosine function. So cosine looks like this. And it kind of continues like this forever and ever, amen. So you're going to need to figure out where cosine is positive and where cosine is negative to figure out this domain. The critical things here are that cosine goes from being positive to negative at odd multiples of pi over 2. So I would say cos x is greater than 0 did they ask us to focus on a particular interval? Sketch the graph of this curve. No, they just want it everywhere. Let's focus just from like 0 to 2 pi. This would be from 0 to pi over 2. So I'd say here 0 to pi over 2. Unioned with 3 pi over 2 to 2 pi, because 2 pi is right here. But their options there are not that simple. So how can I say this better? Let me center this graph over here. Yeah, this is a challenging problem, Fabrice. It's not an easy one. We can exploit some symmetry here. So here's the graph of cosine. I'm just drawing it centered at 0 now instead of over there. This is from like negative 2 pi to 2 pi, which should be good enough for us. Over here is negative 2 pi. This is negative 3 pi over 2. This is negative pi over 2. This is pi over 2. And this is positive 3 pi over 2. So cos x is greater than 0 on, I would say from negative 2 pi up to negative 3 pi over 2, unioned with negative pi over 2 to positive pi over 2, unioned with 3 pi over 2 to 2 pi. So you would start with this as your domain. The truth is it continues like this in this same pattern forever and ever. But I think by restricting our attention to 2 full periods, we'll be able to make this a little more digestible. This is about as simply as we can hope to write this. Right here, I just have, this is the graph of cos x. So this would be our domain that we would start with. intercepts, these are going to be a little bit complicated also. The y-intercept always just comes from plugging in 0. So here y would be the natural log of the cosine of 0, which is the natural log of 1, which is 0. So our y-intercept is the point 0, 0. X-intercepts, we need to solve ln of cos x equals 0. And because this is an equation involving a trig function, it's going to have a lot of solutions. But we can find a few of them. This is the same as saying cos of x is equal to e to the 0. So that's how I get rid of the natural log. I exponentiate, which is 1. So we have an x-intercept every time cos x is equal to 1. And there's infinitely many solutions to that equation, but you can see some of them. One of them is right here at 0. Another one is up here at 2 pi. Another one is back here at negative 2 pi. So these would be at like x equals negative 2 pi, 0, 2 pi, and in general, any even multiple of pi. So I'll track these 3 x-intercepts. Negative 2 pi, comma 0, 0, comma 0, and 2 pi, comma 0. So there's a y-intercept. It's our x-intercepts. And we just have to keep going like this for each one of these things. But it is more complicated. We're lucky here in that we don't have any asymptotes, but we do have symmetry. We have quite a bit of symmetry, actually. So y equals the natural log of cos x. The inside function here, cosine of x, is an even function, which means the whole function is even. If you like, we can say f of negative x, that's the natural log of cos of negative x. And since cosine is even, this is the same as the natural log of cos x. Remember, cos of negative x is equal to cos x. That's one of the identities for the cosine function. And this is f of x. And this is what it means to say that f is even. That f of negative x is equal to f of x. So we have y-axis symmetry. It's also a periodic function. Since cos x is periodic with period 2 pi, f of x plus 2 pi is equal to the natural log of cos of x plus 2 pi is equal to the natural log of cos x, which is f of x. So f is periodic with period 2 pi. So we have quite a bit of symmetry here. There are no horizontal asymptotes. Because the outer function here, the natural log, doesn't have any horizontal asymptotes, but we do have vertical asymptotes whenever the inside of the natural log is equal to 0. The inside of the natural log here is cosine. You know that the natural log function has a vertical asymptote at 0. So this function will have a vertical asymptote wherever the inside of the natural log, which is cos x, is equal to 0. That happens when x is equal to any odd multiple of pi over 2. So that's negative pi over 2. Really negative, I should say negative 3 pi over 2. Pi over 2 and 3 pi over 2. And there's infinitely many, but just from negative 2 pi to 2 pi, those are all of them. From here, we would start on our derivative stuff. So then increasing and decreasing and mins, maxes. I'll show you how to take the derivative here, and then I am going to stop because I gotta get to some other stuff today. Y prime is d dx of the natural log of cos x, which is 1 over cos x times the derivative of cos x, which is negative sine x. So this is negative sine x over cos x. And so your critical numbers would be anywhere that this thing is undefined or equal to 0. So y prime equals 0 when sine x equals 0, which for us would be when x is equal to negative 2 pi, negative pi, 0, pi, or 2 pi. Sine x is equal to 0 at any multiple of pi. And y prime is undefined when cos x is equal to 0, which would be those same numbers we had a second ago. We found those with our vertical asymptotes. So that's negative 3 pi over 2, negative pi over 2, pi over 2, and positive 3 pi over 2. So my number line for y prime is going to be quite busy. I'll put negative 2 pi over here at the end, and then negative 3 pi over 2, and then negative pi, and then negative pi over 2, and then 0. We're actually going to need more space, and then pi over 2, and then pi, and then 3 pi over 2, and then we'll cap it at 2 pi. You may want to just focus on like one period. You may want to just focus on the interval from 0 to 2 pi instead of doing all of this. Because the function is an even function, and because it is, that means anything, once you know it goes on to the right of 0, you get the same to the left of 0. Also, it's periodic with period 2 pi. So once you do 0 to 2 pi, that's really enough for everything. So if I were doing this, Fabrice, what I would do is, at this point, personally, I would go back and start just focusing on the interval 0 to 2 pi, because this is going to get so busy in here. But I hope this is a helpful start. This is a tricky problem, so really take your time here. My advice would be, yeah, to go back, actually, and I know this isn't pleasant, I would go back and start this over, just focusing on the interval 0 to 2 pi. That will make life easier. Say that again?
Can you post this on YouTube?
Can I post what we just did?
Yeah, on YouTube.
Yeah, I can do that. Although again, I'm not sure it's the best thing to follow, because you may want to just focus on the interval 0 to 2 pi. So let me say this, and then I'll post the whole thing. So to solve, to graph y equals the natural log of cos x, pretend, or I'll say restrict your attention to the interval 0 to 2 pi. Just graph that. Because the function is even and periodic with period 2 pi, this is sufficient. Yeah, so I can do that. I can go ahead and post I'll just post the whole office hour and you can look through that last bit. It is a little bit complicated, but it's not out of reach. And if you get stuck on something, go into the Discord. Have you found the Discord for this class? I posted a link for it the other day. I think this would be a good one to talk with your classmates about. Sorry, here it is. This is you guys. If you get stuck on something, just like Katie did this morning, take a picture or a screenshot or whatever and post it in here, and I'll be able to help you out little bits at a time. But it's a long problem and I don't quite have time to go through it all right now. All right, I am going to go ahead and,
Thank you.
yeah, of course. I'm sorry we don't have time to get through all of this, but you can do it. Just same sort of thing, run through that A through H list and be careful on each one. This problem is going to take probably about an hour to get through, but you can do it and it's good practice. And if you get stuck, go to the Discord, I'll help you out.
All right.
All right, Tahara, let's talk about that honors project. How's it coming?
Oh, sorry. I started doing some researches on her. What was the name again? Let me remember.
Was it Sophie Germain?
Mary German.
Oh, Sophie Germain, maybe?
Sophie German, yeah.
Yeah, she's awesome. She was a number theorist from the late 19th century, worked on a lot of things like Fermat's last theorem. She was very cool. How's it coming?
So far good. I just wanted to ask you, what are some stuff you want me to include, like the things that are important to you?
Well, anything that was important to Sophie Germain would be important here. So the first thing that comes to mind for me, let me turn on my screen share. The first thing that comes to mind for me is her work on Fermat's last theorem. So one of her biggest contributions was proving a special case of this very famous theorem called Fermat's last theorem. So Fermat's last theorem says if you take this equation, right, x to the n plus y to the n equals z to the n, that this doesn't have any integer solutions, no whole number solutions if n is bigger than 2. So like, you know, x squared plus y squared equals z squared. This has infinitely many integer solutions. Like if x equals 3 and y equals 4, then z equals 5 works, for example. But if you let the power be larger, like x cubed plus y cubed equals z cubed, this has no integer solutions. And in general, x to the n plus y to the n plus z to the n has no integer solutions if n is bigger than 2. And this statement down here at the bottom, this is called Fermat's last theorem. And it's an incredibly hard thing to prove. This was an open problem. Pierre de Fermat, a French mathematician, claimed to have a proof of this theorem hundreds of years ago, but he never published it. And it took until 1996 when a man named Andrew Wiles, using techniques from algebraic geometry, which is a very modern field of math, definitely did not exist back in Fermat's time, finally came up with a proof. But Sophie Germain was able to prove a few special cases like this one. She was able to prove that this equation has no integer solutions. So I would talk a little bit about her work with Fermat's last theorem. And that's discussed in this paper here. I can give you a link to this. You could use this as one of your citations. But there's also lots of other stuff that she did. So I would research anything that is, you know, just read around about what she has done. So you can search Sophie Germain's big results and see kind of, you know, her Wikipedia page would also be a good place to start. Just see what sort of stuff she did. She
Okay.
did lots and lots of stuff. And then another thing that would be worth talking about is that she actually wasn't able to publish her own results. It's very sad, but mathematics and academia in general used to be incredibly sexist, and women were thought to not be capable of mathematics. And even in her time, even in Sophie Germain's time, she was not able to publish. She was not able to get a degree. She was excluded from all work at universities and colleges just because she was a woman. So she actually
Wow.
had to publish under a pseudonym. She had to send her work to a friend, and then that friend, who was a man, would say, I've got this other friend who has this paper that I want to publish for him. And he would lie and say that Sophie Germain was a man and publish under a different name. So talking a little bit about her life and the challenges she faced due to sexism would be good. Talking about the work she did on Fermat's last theorem would be good.
Okay.
Anything else you can find? She worked with Gauss, Carl Friedrich Gauss, who's one of the bigger mathematicians of that time. He was very, very famous. So I think talking a little bit about her work on FLT, a little bit her issues with the sexism, and a little bit her relationship with Carl Friedrich Gauss would be a really good place to start. But I invite you to read around, definitely read her whole Wikipedia page and see what jumps out to you as being cool, and whatever you want to talk about there, you can talk about.
All right.
All righty, is there anything else I can kind of help you with?
No, that was it. Thank you so much.
Of course, yeah. Before we go, here's the link to our wiki. I would start there. All righty. Okay, cool. I hope you have a good day, Tahara.
Thank you. You too.
Of course, yeah.